the sum, the compact form, we write is sigma. I start with 1, end with n. This is AI, CI. And we have learned the properties of sigma. This is the linearity of sigma. What's wrong? Can't see the screen, okay? Here this is CIAI. We review the linearity of sigma. Okay, linearity of sigma. C is a constant. Then the CAI. C is a constant. We can write it C in the front here. Then sigma I start with 1 and end with n. This is AI. And AI plus BI. We can write sigma AI plus sigma BI. And minus is the same. And we use this property to calculate this is 2AI minus 3BI plus 4. I start with 1 and with 100. That's now. And 6 is A and B. We have calculated. And some special, some formulas. 1, 2, and 3. I think the first 3 formulas are important. The first one is I. Start with 1, ending with n. It's 1 plus 2 plus 3 plus 4, and so on plus n is equal to n times n plus 1 over 2. And the second is 1 square plus 2 square plus 3 square plus n square is equal to, this is n times n plus 1 times 2n plus 1 over 6. And the third one, this is 1 cube, 2 cube, 3 cube plus n cube is equal to n times n plus 1 over 2 square. And with the last one, I think is you can if you meet with this formula, you can remember this. You can search it online, I think. Now we will use here 1, 2, 3. These are 3 formulas to calculate sigma. J from 1 to n, j plus 2 times j minus 1. We make use of linearity and formulas 1 and 2 from above. We have first the j plus 2 times j minus 5 is equal to j squared minus 3j minus 10, right? Minus 10 is equal to, this is linearity. Linearity is j squared minus 3j minus 10. And here, this one, j from 1 and with n j squared. This is a second formula, right? Second formula we know is equal to n times n plus 1 times 2n plus 1 over 6 minus. This is 3. 3 is a constant by linearity. This is just the 3. And this is 1 plus 2 plus 3 plus n. So this is the first formula. We have this n times n plus 1 over 2. And the last one is 10 plus 10 plus 10. We have plus 10 n times. So this is minus 10n. Minus 10n. Then we simplify it, calculate this one, and we have this is 3n minus 9n. We have this is equal to minus 6n, minus 6n over 6. This is n squared, here's n, so this is the final answer. Use this formula. And now we learned the area by inscribed polygons. We consider a ridge are bounded by the parabola y is here. This is y is x squared. This is the curve or equation y is x squared. The x-axis, the vertical line x is 2. We refer to R as a ridge under the curve. Under this curve, this is y squared. So under this curve, between x is 0 and x is 2. Our aim is to calculate its area of AR. So the ridge is R. We want to calculate the AR. This is the area of R. We should partition the interval here because it's under the curve y is x squared and between x 0 and x is 2. So we partition the interval 0 to into n subintervals. We have n subintervals. Each of lengths delta x, we write is 2 over n by means of the n plus 1 points. Yeah, this is the first point is x0. Remark the i's. The second one is x1, x2, x3. This is the xn minus 1, xn. Here, xn is equal to 2. So partition the interval 0, 2 into n subintervals. Each of length 2 over n. We write this delta x. Delta x is 2 over n. Well, thus x0, if x0 is 0, x1, x1 minus x0, this is equal to delta x. The length of each subinterval is equal to 2 over n. And x0 is 0, so we have x1 is delta x is 2 over n. And x2 minus x0, this means the length of this is 2 over n. This length is 2 over n. This is 0, so x2 is equal to 2 times delta x is equal to 2 times 2 over n. x0 is 0, so we have x2 is 2 times delta x. And we get xi, same, for example, this is xi. Xi is equal to I times delta x. So it's equal to 2i over n. And xn minus 1 is n minus 1 times delta x. We have n minus 1 times 2 over n. And the last one, xn is 2. So it's equal to n times delta x is equal to n times 2 over n is 2. We have n plus 1 points. And then we consider the typical rectangle with base xi minus 1 xi. Here, this is x. Consider this is x0, x1, x2, and xi. If I write xi minus 1 here, xi here, the base is xi minus 1 xi, and the height is fxi minus 1. Fx is equal to x squared. Fx is x squared. So xi minus 1 is xi minus 1 squared. Its area is here. This is the base is xi minus 1 xi, and the height is fx. The height is fxi minus 1. This rectangle, consider. So the area is equal to the height fxi minus 1 times the base delta x. See the upper left part of figure 7. The unique Rn of all such rectangles forms the inscribed polygon shown in the lower right part of figure 7. Yeah, this is the first rectangle, the second one, the third one, this one and this one, we have this. The unit Rn of all such rectangles forms this is called an inscribed polygon. The area ARN can be calculated by summing the areas of these rectangles. ARN, this is the area of first rectangle plus the second one. This is the first one plus second one plus this third and plus the last one. Here, this is the last one. And fx here fx I delta x. Now we calculate this one fxi delta x. Fxi, this means xi square times delta x, and xi square we have no xi is 2i. Here is 2i over n. 2i over n. So it's 2i over n squared times 2 over n. Right? Times 2 over n. So we simplified it is equal to h over n cube I squared. Right? I squared. And we have this is we write this is the sum of n. So we can write like this in a compact form. We write sigma. This is fxi minus 1. Or we write this is xi times delta xi. Because the first is x0, so this means I from 0 to the last one is xn minus 1. So it's equal to n from 0, start with 0, end with n minus 1, right? I write like this. Or we can write, we can, because we know fxi delta xi. So fx0 delta x, fx0 delta x is equal to, this means I is 0. I is 0, this is 0 over n squared times 2 over n plus here x1, this is 2 over n squared times 2 over n plus I is 1, I is 2, so it's 4 over n squared times 2 over n. Then we plus the last one, so it's equal to this one. Calculate is equal to this one. This is because here this is 8. 8 over, this is 8 over n cube I squared. Oh, right. Okay. This. Which one? Your I give you only one. I give you only one chance, okay? Next time, please. I have no excuse. I won't change it. Now give you one chance. Outside, I give you one chance and I change it. Your station is private, okay? last time. No, this time. Last time I want to change it. Just this time. Oh, this is your last time. Okay. I change it. Your station is present. Okay. Now we have x fxi delta x is 8 over n cube as square. So we have fx0. This means fx0 delta x I is 0. So it's 8 over n cube 0 square plus 8 over n cube 1 square plus 8 over n cube 2 square plus last one is here xi square. This is I is n minus 1. So it's 8 over n cube n minus 1 square. Right? And this is I from 0, start with 0, end with n minus 1. So this n minus 1 square. And I have this factor is 8 over n cube. This is 0 square plus 1 square plus 2 square plus n minus 1 square. Right? And by the second formula, we have 1 square plus 2 square plus n square is equal to remember this? Is equal to n is equal to second formula. Is equal to this one. N times n plus 1 times 2n plus 1 over 6. N times n plus 1 times 2n plus 1 over 6. Right? Over 6. But here this 1 square plus 2 square plus n minus 1 square. This is not the last one is not n square, right? So we just replace n by n minus 1. This means we have right here or right here. This is 8 over n cube times this is equal to n replaced by n minus 1. N minus 1 is n minus 1 plus 1. And 2n minus 1 plus 1. Okay. So it's equal to 8 over n cube times 6. This is n minus 1 n. This is equal to 2n minus 1. 2n minus 1 we have here. Let me take it. Yeah. Yes, right. The same. Yeah, the same. From this is the same. Right? And the n minus 1 times n times 2n minus 1 is equal to 2n cube minus 3n square plus n. This is over n cube. So we calculate is 4 over 3. 2 minus 3 over n plus 1 over n square is equal to this one. This is the area of inscribed polygons. Right? Inscribed polygons. And then remember this. We conclude that AR, this AR, the area of this rate, AR is the limit n approaches infinity. ARN is equal to here. ARN is equal to this one, and n approaches infinity. This is 8 over 3. This is a constant, so it's still n 8 over 3. And we n approaches infinity, 4 over n approaches 0, right? And 4 over 3n squared over to 0. So it's 8 over 3. And the diagrams in figure 8 should help you to realize what is happening as n gets larger and larger. Here we have 7 rectangles, 14, 28. We can find ARN is approaching AR. Right? ARN is approaching AR. And now we will use the circumscribed polygons. Perhaps you are still not convinced, right? AR is 8 over 3. We can give more evidence. Consider a rectangle with base xi minus 1 xi, and the height is fxi is x squared. In script, we use height is fxi minus 1 is equal to xi minus 1 is square. We choose the left endpoint, and circumscribed polygons, we choose the right endpoint, xi. Right, xi is xi squared. Its area is fxi delta xi. Right, fxi delta xi. The union Sn of all such rectangles forms a circumscribed polygon for a right arc, as shown at the lower right in figure 9. This one. This is the first rectangle, the second rectangle, the third one, the first, and they formulate the subscribed polygons. The area ASN is calculated in analog with the calculation of ARN. So ASN is equal to the base is the first one is x0, x1. So it's fx1 times delta x. The second is fx2 times delta x. The last one is fxn times delta x. As before, we calculate fxi times delta x is equal to fxi is xi squared. Delta x, we know, is still 2 over n. So 2 over n. And xi, we have xi is I times n 2. Remember, this is still xi squared times 2 over n. So it's equal to 8 over n cubed times I squared, right? Xi. We first partition this interval into n subintervals. We have n plus 1 points. So xi is equal to I times 2 over n. And then we have ASN. ASN is equal to fx1 delta x. This means I is 1. So it's 8 over n cubed 1 square plus 8 over n cubed 2 square plus the last one is 8 over n square. Xi is n. And we have the factor is 8 over n cubed. This is equal to 1 square plus 2 square plus n square, right? Plus n square. Then we use the formula 2. We have this is equal to 8 over n cubed times 1 square plus 2 square plus n square is equal to 6. This is n plus 1, 2. 2n plus 1. 2n plus 1, right? And then here, this is, here, this one, this one. And then the special sum formula 2. This is 2n cubed plus 3n squared plus n. And simplified is 8 over 3 plus 4 over n plus 4 over 3n squared. Again, we conclude that AR is the limit n approaches infinity ASN. We calculate the limit is still 8 over 3. 8 over 3. Okay. So we use circumscribed polygons to calculate the area is still 8 over 3. So the area below y is x squared, between x 0 and y 0 is 8 over 3. Now another problem we have seen. Suppose that an object is traveling along the x-axis in such a way that its velocity at t is given by, here we have velocity, v is ft is equal to 1 over 4 t cube plus 1 feet per second. How far did it travel between t is 0 and t3? This problem can be solved by the method of differential equations, but we have something else in mind. Our starting point is a familiar fact that if an object travels at constant velocity k over a time interval of length delta t, then the distance traveled is the velocity times the time interval delta t. Right? This is travels at constant. But here, this is the velocity is 1 over 4t cube plus 1 is not a constant. But this is just the area of a rectangle, the one shown in figure 10. Here, this is the k times delta t. And so next, this means we consider the given problem where v is 1 over 4 t cube plus 1. The graph is shown in the top half of figure 11. Here, this is the graph. Y is 1 over 4 t cube plus 1. Partition, still, we should partition the interval 0, 3. This is from time is 0, from 0 to 3. Partition 0, 3. We have n subintervals of length is delta t is 3 over n by means of points. T0 is 0, T1, T2, and Tn is 3. Then we consider the corresponding circumscribed polygons Sn displayed in the bottom half of figure 11. This one. This is the first rectangle, second rectangle, third one. Its area ASN, right? ASN should be a good approximation of the distance traveled, especially if delta t is small, since on each subinterval the actual velocity, this actual velocity is almost equal to a constant. So the value of v at the end of the subinterval. Moreover, this approximation should get better and better as n gets larger. We are led to the conclusion that the exact distance traveled is this limit, ASN. That is the area of the range and the velocity curve between T0 and T3, right? Well, if the velocity is a constant, so the distance is the area of this rectangle. And here, this is not a constant, so we can partition interval 0, 3 into n subintervals. And on each subintervals, we can use the area of this triangle, right? Rectangle. We can use the area of this rectangle to approximate the distance, right? It's not the same. We can approximate. You don't understand? This tells us how to calculate the. Do you know the first one? It means we want to calculate the area of this ridge, but we don't have the formula because we know how to calculate the triangle, the area of the triangle, the polygon parallelly. 我们知道计算长方形、正方形以及三角形的面积 ，but we don't know how to calculate the area of this irregular ridge. But how? So we can use sub-rectangle, sub-rectangle, inscribe the rectangle areas and the circumscribe polygons to approximate the area of this ridge. Now, you know this. We learned. No, I won't change that. What's your Chinese name? I remember I have changed the one student station. Now, this is the last time. You just listen to me. Last time we introduced how to calculate the ridge with a curved boundary, right? With a curved boundary. For example, this is a circle. How to calculate the ridge? We can use this what? Polygons. We can use consider a sequence of inscribed polygons that approximate the curved ridge. We can use this rectangle approximate the area of this circle, right? And the size when we the size is increased, the size increased. We have this the second polygons to the area of the second polygons to approximate the area of this ridge. Here is the P2. We can say this is and this means for the circle we consider regular inscribed polygons with 4 sides, 8 sides, 16 sides. Now, we can find the area of the circle is a limit as n approaches infinity of the areas of Pn, right? Yeah, when the size increase, when the size gets increase, when we increase the size, the area of rectangle inscribed polygons approximates the area of the circle. This is inscribed. And Archimedes also used circumscribed polygons here, this rectangle to approximate it, right? And we also increase the size. This is 1, 2, 3, 4, 5, 6, 7, 8 with 8 sides to approximate the area of this circle. And here maybe this is 8, 12, 1, 2. Because it's easy to calculate the area of polygons. No, we can calculate the area of rectangle, the area of the parallelogram. They are all polygons, regular polygons. We can calculate this. And also, no, polygon, we can partition it into many these rectangles. A1, we can calculate A1 plus A2 plus A3 plus A4 plus A5. We have this is A. So this size with curved boundary, we use regular polygon. Regular polygon. Okay, and then here this is circle, but now now if we face the width here like this, if we face with this ridge, this is also with curved boundary, right? This y is x square, y is x square. You can also use polygons. And we partition 0, 2 into n subinterval. This is x0 is 0. This is x1, x2, And we have here, we get a rectangle. A rectangle, we use the base here. This is the base is first. The base is x1, x2 is the first one, and the height. Yes, we find the polygons. Yes, we find the areas of these polygons, and then we take limit. We get the area of rate R, and we find here this rectangle polygons. And the first one, maybe this is x3. x3. The base is x2, x3. The height is fx2. This polygon, right? And maybe this is x4. Here. This is x4. x5. And the last one, this is xn minus 1. 2 is xn, right? So we have this polygon. Now we find the areas of these polygons is approaching the area of the range R. So we calculate ARN. Here ARN, the area ARN. We calculate this area of ARN. Okay, we will try to find the area of ARN. So you should know that the base is xi minus 1 xi, and the 高度应该的 height, right? The height is fxi minus 1. Rn means, what is Rn means the range. Which Rn? Rn means the Rn means a rectangle. R means a rectangle. Rn means rectangle. Okay? Rn. This R1, R2, R3, Rn rectangle. The union of Rn of all such rectangles. Now this is sentence. The union Rn of all such rectangles forms the inscribed polygon shown in the lower right part of figure 7. Right? Okay, we calculate is the areas of this rectangle is equal to this one. And then we take limit. This means we let limit n approaches infinity. Take limit n approaches infinity. We find this is 8/3. Here we use inscribed polygons. Now we can also use here this subscribed. Now this figure 8. You can help you to visualize what is happened as n gets larger and larger. N gets larger and larger. We can see AR8. This is 28. This means we have 28 rectangles. We have 28 rectangles. This means n gets larger and larger. ARN is approaching AR. And now we use circumscribed polygons to approximate the area. Circumscribed. So we should notice that here the base is still xi minus 1xi, but the height is equal to fxi. Here, fxi. This is fxi. This is y is xi square. This is the curve. So we have the height is this. The base is xi minus 1xi. The height is fxi. So the area we have is fx1 dx plus fx2 dx plus the last one is fxn dx. And we calculate this. We have this is 8/3 plus 4/n plus 4/3n square. Right? And then we continue calculate the limit. Limit n approaches infinity. We find is 8 over 3. It's the same with the second inscribed polygons, right? Inscribed. So we have the area AR. AR is equal to 8 over 3. And by this way, we find the area with curved boundaries is 8 over 3. This one. Curves on screen. Do you understand this? Always, yes, always. Now this is geometric respect. Now we have another problem. It's almost is the same thing. We have suppose right object is traveling along the x-axis in such a way that its velocity at time t is given by 1 over 4 plus 1 feet per second. How far did it travel between t0 and t3? Okay, and this problem can be solved by the method of differential equations, but we have something else in mind. The starting point is a familiar fact that if an object travels at constant velocity, this means if v is k, it's a constant velocity over a time interval of length delta t. So then the distance traveled is k times t. So the distance s we write is k times delta t, right? K times delta t. But this is just the area of rectangle, the one shown in figure 8. See, if the length of this base we write is delta t, and the height is k. So k times delta t, just the distance is also the area of this rectangle, right? But now we want to solve when v is not k, not a constant, is 1 over 4 plus 1, right? So then we give this is a curve ft, this is a curve. Ft is 1 over 4 plus 1. And we consider the time is between 0 and 3. So this is 3. This is 0 between this one. Okay, between this one. Yes, right, it's complicated. But here, this is not the real way we calculate the area and the distance. We will use definite integral to calculate it. Okay, this is just why and this is just why we can use definite integral to calculate the area and the distance. Okay, I just explain the reason, but we don't use this method to calculate it. Okay. Here, so ASN. This means we are led to the conclusion that the exact distance trapped is this one. It's ASN. It's also the why we find area. Maybe in the reality, you face this problem. How can you solve it? Right? Because here you only know how to calculate the area of the triangle, parallelogram, and the rectangle. But when you face complicated problems, maybe it's not a regular polygons. Is area with the ridge with the curved boundaries. How can you solve this area? How can you get the area? Right? How can? So this is what I told you. And then is the area of ridge. No, the distance is just the area of a ridge and the velocity curve between t0 and t3. Is right. So we can also use the circumscribed polygons and inscribed polygons to calculate the distance. Here, ft, right? This ft is 1 over 4 plus 1. Now we use the circumscribed polygons. Circumscribed polygons first, we also partition 0, 3 into n subintervals. We get T0 is 0, T1, T2, Tn minus 1, Tn is 3. And we get delta T is 3 over n, right? 3 over n. And we use FTI is equal to FTI is equal to FTI is equal to, which is FTI is 1 over 4 TI cube plus 1. And we can get TI use the same way. We can get TI. TI, as noted, TI is 3i over n because we partition it into n subintervals. So with the links is 3 over n. No. Actual velocities are equal to constant no. So that's why we explain this. Okay. So the area of the ice rectangle is this is FTI. FTI times delta T. We calculate FTI, and TI is 3i over n. This is T replaced by TI. It's 3 over n. We have this one. And we calculate the area ASN is FT1 delta T plus FT2 delta T plus FTN delta T. And we calculate this from I start with 1 and with n. I start with 1 and with n is 3 over n. And we use the special third formulas. We have this one. Special sum formulas 3. Special sum formulas 3. And then we take a limit n approaches infinity, limit n approaches infinity. Can solve this limit? This one, the limit n approaches infinity. 8 over 81 4. This is times is n for 1 is n square, n plus 1 square over 4 plus here is the 3. Can you solve this limit? Yeah, please tell me your answer. This limit is equal to 81 over 4. 81 over 4. Do you know how to calculate this? Here we know that this constant is it's 81 over 16, right? Times means we calculate this one. N approaches infinity is n square, n plus 1 square over n 4 plus 3. This one, right? And please tell me this one. The limit is equal to 1. We can divide both by the highest power, right? The highest power. So it's n is equal to 8, 116. Limit n approaches infinity is divided by n power 4. So divided n by power 4 is 1 times this is n plus 1 over n square. This is 1, right? Oh, we can cancel. This is n square. Oh, right. So it's equal to plus 3. So the final answer is 8116 plus 3. Okay, yes. 18 1 over 16 plus 3. So the object travel about 80.06 feet between T0 and T3. What was true in this example is true for any object moving with positive velocity. The distance traveled is the area of the ridge and the velocity curve. So we will have some concept review. 1, 2, 3, 4. The value of I from 1 to 5 to I. Calculate.热不热？我觉得有点热，好看。啊！51212，你看看又死机了，怎么改呢？又死机了，551212。What's your Chinese name? Do you have a Chinese name? Are you 侯赛德？你是侯赛德吗？No, I can't. Change it because maybe 死机了。First time. 死机了，I can't change it. Maybe first time it does not influence your regular performance. Okay. So don't worry. Yeah, maybe you are present. Okay. 什么玩意儿 ？Waiting for a while，死机了。OK。唉。 Hello. Hello. Only once. Okay, only one. I change
Yes,
your
Lashi, yes.
position. Okay.
Yes.
Next
Hussein MD
time,
Arafat.
please tell you. Tell me.
Yes, Lashi. Okay, Lashi. Lashi, I'm Hussein MD Arafat.
What?
The first one, Hussein.
Hello, let's do concept review. The first one, the value of, please tell me your answer. The first one, the value of 2I from 1 to 5. 4. It's 4. It's 4. What's your answer, Julia? It's so easy, you can have the answers. The first one, anyone gets the answer? $30. I think 30 is right. By linearity, we write this is I from 1 to 5. We write I in the front. This is I, right? So it's equal to I is 1 plus 2 plus 3 plus 4 plus 5. It's equal to 2. We use the this one. We use the special sum formula 1. 1 plus 2 plus 3 plus 4 plus n is equal to this is n 5 times 6. So it's equal to 30. Right? It's 30. It's not 4. You can calculate one by one. It's not 4. I don't know why you write it 4. And this one is equal to 2 plus 2 plus 2 plus 2 plus 2. So it's 10. Right? It's 10. Okay. And the second one, AI is 9, 7. So the value of this one is equal to 13. So it's 3 times 9 minus 2 times 7. So it's equal to 27 over. So it's 13, right? And the value of this is sigma. I start with 1 and with n. This is AI. Plus I start with 1 and with 10, 4. So it's equal to, here is 9 plus 40. It's 49, right? It's 49. Yeah. The area of a polygon underestimates the area of the ridge, whereas the area of overestimates this area. So the first is underestimate. Underestimates. So it's inscribed polygon. And this one is circumscribed polygons, right? And the exact area of the ridge and the curve. This is the greatest integer function. between 0 and 4 is last one. Maybe give you a little time to think about the last one. To remember the curve of this greatest integer function. 0, this is 4, this is 1, 2, 0, this is 4. 1, 2, 3. The greatest integer function, x. If x on the interval 0, 3, at 0, 1, please tell me the greatest integer x is equal to 0, right? It's 0, 0. And Vx is 1, so it's equal to 1. This is a circle, this is 1. 1, 2 on this interval is equal to this one. 2, 3, this is equal to 2, 3 here. And 3, 4. 3, 4. So it's under the curve and this curve between 0, 4. Between 0, 4. So the ridge under this curve. So the area, we have 3 rectangles. The sum of the 3 rectangles. Right? The base, because this is not a rectangle, just a straight line. So the area, this part is the area 0. Is 0. So this one is equal to R1, right? R2, R3. So AR1 is plus AR2 plus AR3 is equal to the base, the length of the base. The length of the base is 1 times the height is 1 plus the base is 1, the time the height is 2. This is plus 1 times the height is 3. So it's equal to 6, right? It's equal to 6. Let's check your answer. 6. By 6. Any questions for concept review? No? No questions? Okay. Oh, and maybe we will learn the Riemann sums. 黎曼河. And consider function f defined on a closed interval AB. It may have both positive and negative values on the interval AB. Here, A, B on interval. And it does not even need to be continuous. Its graph might look like something like the one in figure 1. When consider a partition P of the interval AB, here is AB, AB, right? We have a partition P of the interval AB into n subintervals, not necessarily of equal length. Before, we always have the equal length. But here, not necessarily of equal length. By means of points, A is A0. This x1, x2, x3, x4, x5, and xn minus 1, xn is b. And we write delta xi. Delta xi is equal to xi minus 1. The delta xi. On each subinterval, xi minus 1, xi. Example, is on each subinterval. This is AB. AB, we have partition. For example, this is the point xi minus 1. This is the point xi. On this subinterval, we can pick an absolute point xi bar. Absolute point. Example, this is the absolute point xi bar, which may be an endpoint, left endpoint or right endpoint. We call it a sample point. This is a sample point for an S subinterval. An example of this construction is shown in figure 2 for n is 6. N is 6. Here, this means we have A is x0, x1, x2, x3, x4, x5. The last one is x6, is B. And delta xi is still xi minus xi minus 1. And we choose a sample interval, a sample point for the S subinterval. And for example, in the first interval, we choose sample points xi bar. This is the second subinterval, right? We have a sample point x2 bar, x3 bar, x4 bar, x5, x6. And have the length is delta x1, delta x2, delta x3, delta x4, delta x5, delta x6. They are not necessarily of equal length. Now, we call the sum. We have, for example, the first sample point x bar, x1 bar. We have a value is f x1 bar. Fx1 bar. So if we take this is x1 bar times this is delta x1, the length of the first subinterval, and plus f x2 bar delta x2, and plus the last one is f xn bar times delta xn. We write this RPN. This is the Riemann sum for f corresponding to the partition P. Its geometric interpretation is shown in figure 3 here. This is A, this is B, the x0, x1, x2, x3, x4, x5, x6. We have here x, we choose x1 bar. Remember, I hope you remember this x1 bar. Right? So fx1 bar, let's see, fx1 bar. Fx1 bar is this. Thanks, right? And then we times delta x1. Delta x1 is the length of the first subinterval. So the delta x1 bar. Delta x1 is equal to x1 minus x0. So the base is x0, x1. The height is fx1 bar. The product is equal to the area of this rectangle, right? Area of this rectangle. We write this is, and we choose another sample point x2 bar. We have fx2 bar times delta x2 is equal to the area of this rectangle. And this one is sum together, and this one, and this one. A5, and this is A6. So a Riemann sum interpreted as an algebraic sum of areas A1 plus A2 plus A3 plus A4 plus A5 plus A6. Now we can use the sum of these to approximate the area of the region under this curve, right? We can see under this curve. Under this curve, right? And between A and B, can approximate it, right? Approximate it. And so, for example, we evaluate the Riemann sum for f(x) is x squared plus 1 on the interval -1, 2, using the equally spaced partition points. -1, -0.5, 0, 0.5, 1, 1.5, 2, with the sample point xi bar being the middle point of the S subinterval. Maybe we have no time to explain it. I think we have. Maybe you can figure for it. We explain it tonight, okay? Because I think today, right, is a little complicated. Right? I hope you understand what I have signed. Okay. Hello. Huh? What? The list. Yeah. What list? Yes, yes, you are present. Yes, you are present. Yes.
老谢